All right, welcome to Computer Science 4422 software testing. Today we're going to talk about input space partitioning. And so outcomes of today's lecture is that, one, you'll understand the basics of input space partitioning. You'll be able to partition an input domain, be able to model an input domain, and then today and tomorrow you'll be able to understand how parameters and their characteristics can be used for this, and understand multiple ISP-based criteria. So, inspirational quote: just because you've counted all the trees doesn't mean you've seen the forest. So I want you to be hopefully thinking about this, or let this inspire you while you're thinking about input space partitioning. Okay, so model-driven test development, MDTD, is broken across 4 different spaces, and so we're looking at particularly input space today. So, benefits of ISP, right? They can be equally applied at various levels of testing. That includes unit, integration, and system. It's relatively easy to use and apply with almost, even if you have no automation. It's easy to adjust the procedure that we use for this in order to get more or fewer tests. And it does not require implementation knowledge to be able to do this. All we need is just to know what the input space is to our program. And so that means that we kind of need to know what's going on here, right? So the input domains that we're talking about are basically all the possible inputs to a given program. And so the problem here is that even for small programs, this becomes effectively infinite, right? Because the input domain tends to be extremely large. And the problem here is that testing, fundamentally, we're focused on selecting finite sets of values from the input domain. So for this type of testing, what we want to do is use our input parameters to define the scope of our input domain, okay? And then that means we're looking at things like parameters to a method, data read from a file, global variables, and user-level inputs. And we're going to take those input parameters, and then we're going to partition them into regions, which we will call blocks. And then, in order to get down to a finite set of values, we're going to select at least one value from each of these blocks, okay? Now, what does that really mean? Well, partitioning domains is actually not too difficult of a thing to understand. Essentially, we start with some domain D, okay? And then we're going to try to develop a partition scheme Q for D, and that partition Q defines then a set of blocks, the set B sub Q, which is equivalent to block, so B sub 1, B sub 2, all the way through B sub Q, okay? And then the partition must satisfy 2 properties. The first is that the sets within the partition must be disjoint, in that there can be no overlap. So if we want to think about this mathematically or formally, that means that B sub I, some block B sub I and some block B sub j, their intersection must be the empty set. And for all I not equal to j, B sub I and B sub j are both elements of the set B sub q. Okay. We also have to meet the condition of coverage, right? All blocks must, the total of all the blocks must cover the domain D. So that can be written as the product across all B, product across, the union across the set, the subsets of B sub Q, right? For all B and B sub Q, must be equal to the set D, if that makes sense. I hope it does. So there's an in-class exercise, but for those of you who are watching the video and or AO, what you can do is sit down for a minute and think about how we might partition the set of integers, okay? That is, we want to partition them into blocks such that each block seems to be equivalent in terms of testing. And then make sure your partition is valid. That means it has to be pairwise, disjoint, and complete. All right? So I'll give you, take a few minutes, pause the video, and then when you're ready, come back and we'll discuss this. Okay. So in order to think about this, there are several that possibly could come to mind. One might be that we can break the set of integers into the set of negative integers, the set containing just 0, and the set containing all positive integers. These are effectively equivalent in terms of testing, right? And they are pairwise disjoint and complete. Another approach might be to think of it as, well, how might we break these down? Well, we could also think of, we have even and odd, right? Negative and positive are characteristics of integers. Other characteristic might be even or odd, okay? Now, so we break that down, and then we have the same type of choice, right? So we have all the even numbers, all the odd numbers, and then the question becomes, do we need to talk about 0 in this, or can we consider 0 to be an even number? So I would consider that 0 is an even number, and then you have even, odd, or you could do the positive, negative, 0, or you could do, it depends on what you want to do. Less blocks means less tests, so bear that in mind. All right. Other things, like someone might come up with the idea that we want to look at prime versus non-prime numbers. That's not going to be a equivalent the size of those blocks or the partitioning will not be equivalent in terms of testing. So, and furthermore, how do you define? We know how to define whether a number is prime or not, but how do we identify all the prime numbers? That's another issue. All right, and also, well, I'm not going to get into that. But anyway, so now, once we have partitions, right, we have a couple assumptions that we have to make in order to use partitions. So one of the first assumption is that we're going to choose a value from each block, right? Each value is then assumed to be equally useful for testing. The application to testing is that we want, in order to do this, we want to find characteristics in the input, right? So these parameters, semantic descriptions, etc., such that we can partition each characteristic, and then we choose tests by combining values from these characteristics, okay? Example characteristics can be whether input X is null, order of the input list F, so is it sorted, inverse sorted, arbitrary, or whatever, minimum separation of two aircraft, input device, was it DVD player, CD player, VCR, computer, what is it? And then, if we're breaking down people, we could partition them by their hair color, height, major, age, variety of different characteristics, all right? So now, once we've figured out the characteristics that we're going to do, then we need to start choosing or defining our partitions. And it seems like it's going to be obvious or easy to do, but it's actually extremely easy to get it wrong, right? For example, consider one of our previous examples, which was ordering of elements in list F, okay? We start out and we might say, well, what we might want to do is break these down into sorted in ascending order or sorted in descending order, and maybe we just have another block that's arbitrary, okay? But if we think about this, if we have a length 1 list, right? Okay, so it contains the number 14. Then this list itself is in all 3 blocks. And therefore, disjointness is not satisfied. So instead, what we might want to do is think about how we can actually make this so that the characteristics only address just one property, okay? So we create C1, which list is sorted ascending, okay, this is the characteristic, and then we break that into 2 blocks. It's either true, the true block, or the false block, where true it's ascending, or false it's ascending, okay? And then same thing for descending, right? We create block B1, which is false, and B2, which is true, all right? And this means that so across these we end up having it's either ascending or it's descending, but it's never both, all right? So now, and then with this, even a list of 1 can be in only one of these at any one time. One block at any one time. So we'll look at that. But anyway, when we're thinking about this, when we're trying to model the input domain, okay, we have essentially 5 steps. The first step is to identify the testable functions that we want to actually work with. 2 is to find all the inputs and parameters, okay? And then we can use that to move from implementation level to design abstraction level. If you recall the MDTD kind of flow graph that talked about that, we were there's the implementation level and then design abstraction level, and then we moved from code or some artifact, and then we extracted a model, in this case the input domain model, and then from that we generate our test requirements and all this type of stuff, okay? So then step 3 is to model the input domain. This is entirely at the design abstraction level. Then we move to step 4, which is we have to use a test criterion to choose combinations of values. And that's still this is getting us to the point where we have our test requirements. And then we finally refine our combination blocks into test inputs, which then brings us we get those test inputs. Now we're at the implementation level. And now we can then use that to develop our automated tests. All right, so this is another in-class exercise, but for those of you watching the video and our AO students, what I would like you to do is to go to Chapter 1. There are several different examples. You can also go to the book's webpage, and they have them all there. And then I want you to find one of these, and then look into and think about what might be a good set of characteristics and a way of partitioning, creating the input domain model for this program, okay? It should take you about 10 minutes to do it, maybe a little bit less. But anyway, pause the video, do that, and then we'll continue forward. Okay, now that we've returned. So for steps 1 and 2, we'll talk about an example of doing this partition in a bit here. So for example, for steps 1 and 2, we have to then identify the functionalities, parameters, and characteristics, okay? This is a creative engineering step. And the more characteristics we derive, the more tests we end up having to do. Okay, so for interface-based approaches, we need to translate parameters into characteristics. Candidates for characteristics tend to be preconditions and postconditions. For example, the list can't be empty, or we return an empty list, or whatever it might be. Relationships to constants and among variables. Okay, so like, for example, if x has to be greater than 0 and x is not equal to y, we need to think about that. And then we also need to think about the software behavior, not its implementation, but what it's supposed to do. So element is in, make sure that the element's in the set, whatever it might be. That's an example, right? And then we should not use the program source, right? Characteristics are based on the input domain only. We're not needing to look at how this thing is going to be implemented. We just need to know what it's supposed to do. Later, we will look at program source when we focus on graph and logic criteria. But here, we don't need to worry about that. And so it's better to start with more characteristics and have few blocks rather than few characteristics with lots of blocks. The goal of this is to minimize the number of mistakes and to minimize the number of tests that we need. Okay? So, for example, we have this. So there is a triangle.java on the book's webpage and in the that you can use to think about this. But there are 2 classes: triangle type in triangle, right? And then triangle type in triangle. There's this trying method, okay? And so you can also find this on Moodle. I will put these on the source code online. But in essence, what you end up having is you have this enum triangle. It has 4 different types, and we have the static triangle trying, which takes in 3 values: side 1, side 2, side 3. Okay, and they represent the lengths of the side of the triangle, and then it will return the appropriate enum value based on what it sees. Okay, so the IDM for each parameter is essentially identical, right? They're all integers, and then a reasonable characteristic would be the relation of the side with 0. Okay. So now, we also can consider the method from triangle type again, where we could think about our parameters all together representing a type of triangle. And so then the IDM would then combine all parameters together, and the reasonable characteristic might be type of triangle. Okay, so this is the second way of doing it, but we're going to focus on that first one, okay? Before we get there, though, I want you to think about breaking down this find element concept, okay? Note that, so we have this function find element takes in two values, a list and object element, and the effects of this executing is that if the list or element is null, it throws a null pointer, else it returns true if the element is in the list and false otherwise. So I want you to take a few minutes and identify the functionalities, parameters, and characteristics for the find element method, and then so pause the video and then take let's say 2-3 minutes, do this, and then we'll come back. Okay, so assuming that you've done that, right, we can break this thing down just so we can see this. The parameters and characteristics for find element were this. We have two parameters. We have a list and an element. Okay, so parameters are found. The characteristics based on the syntax, right, is that it says that if the list or element is null, we throw a null pointer, right? So we look at the list. We're looking at the list, and then we have the element. Okay, so if the list is null, we can say it's either true or false. Okay, that's going to be null, and the list is empty. It's either true or false. And then we have characteristics based on behavior. This is about the element, right? So either the element is in the list, and then it depends on. So if the list is null or empty, then we don't worry about it. And then we have the concept of the number of occurrences of the element in the list. So in this case, we say 0 meaning it's not in the list, 1 meaning it's just one of them, and then greater than 1. And then we have to ask the question of, does it occur first or last in the list? Okay, true or false, right? And from that, we can derive all the values we need, okay? There we go. So we have a syntax-based characteristic and a behavior-based characteristic. All right, back to the steps, right? So this is back on trying, okay? And so modeling this is back to the kind of understanding the steps, right? So now we need step 3, we need to model the domain, right? And so we need to partition characteristics into blocks and values, and we need to understand that this is a very creative engineering step, right? There's no scientific approach to tell you what exactly the characteristics should be and how we're going to break them into the blocks, okay? But we have to understand that if there are more blocks, that means we're going to have more tests. And we need to understand, we also need to think about that partitioning can flow directly from the characteristics, and both steps can be done together. So we should evaluate them separately, but fewer characteristics can be used with more blocks and vice versa. So you can kind of, you have to find the right balance point when you're doing this. Continuing with this modeling the input domain, there are strategies for identifying values, right? So we need to include valid, invalid, and special case values. We need to think about subpartitioning some blocks. We might want to think about boundaries on domains, how we might explore those. We want to include values that represent what we might call the normal use or happy path. And we need to try to balance the number of blocks in each characteristic just so that makes it easier to evaluate. And then once we're done with all that, we have to check to make sure that our partitioning is complete and disjoint. All right. So now, go back to trying, right? So this is the IDM based on, so we can create a mapping based on syntax, right? That was the original one. Where the trying has one testable function and 3 input integers. So then we said that we were looking at this in relation to the sides, each side 1, 2, and 3 to 0. And so if we do that, our characteristic is relation to side 1 to 0, side 2 to 0, side 3 to 0. And we break it down, each one of these into 3 blocks. B1 block is greater than 0 for each. B2 block is equal to 0 for each. And B3 block is less than 0 for each. All right. Now, so we're going to end it there for this, and we'll let you guys think about this. Right. We've gotten basically the first step kind of done. Right. The first 2 steps done. Okay. When we come back in the next lecture, we will continue this example. All right. So if there are any questions about this or concerns, you stop by my office hours on Zoom. You can also come, send an email to me and set up an external meeting, right? Come to class, talk, ask questions, etc. Anyway, you guys have a great day, and I'll talk to you all later.